Try and go up. Okay, and back down.
This is the most complex robotic arm in existence today. You can control that using thought from the brain.
I could build that. Hey, my name's Alex and I've had a bunch of free time recently, so I thought what better way to spend my time than by helping the medical field. Now, I don't know anything about medicine, but I do know how to code and I know a bit about robotics. So I got to researching it. These big companies have been building these so-called mind-controlled prosthetic arms. Come take a look at this. They cost $500,000. That's like 3 tanks of gas in the US. And on top of that, they come with several issues, like you need an invasive surgery and months of practice just to be able to use them. So the solution became painstakingly clear to me. Build one of your own. Mine is going to be super cheap, you won't need surgery, and you won't need months of practice to be able to use it. Come on. This is the final, not so final prototype finger. It's not final because it doesn't really look like a finger, but let me explain how it works. So there's a string that runs with the front of the finger connected to a servo motor, an elastic band in the back. The elastic band snaps the finger back into place, and the servo motor rotates to contract the finger. When the servo motor rotates back, finger straightens. Pretty simple pulley system. Now, I know what you're thinking. Alex, what about the mind control part? Or maybe you're thinking, mind control doesn't exist. Well, mind control does exist, sort of. So, basically, there's this technology called electroencephalography, or EEG for short. EEG basically allows us to roughly read the electrical activity in the brain. By doing so, you can tune in to brainwave frequencies. By looking at certain frequencies, we can see when the brain is more focused or attentive on doing a task. Now, this technology isn't going to allow us to move specific fingers or do very intricate movements, but we can open and close the hand whenever we want, just by a thought. So now let's write some code and connect it to our prototype. Let's go. Before we get into the live demonstration, let me first show how everything is set up. So we have an Arduino Uno connected to a Bluetooth module, and that's all connected to our prototype finger. Now, this Bluetooth module will receive data from our EEG headset. The headset I'm going to be using is a NeuroSky Mindwave Mobile 2, simply because it's just the cheapest one I could find, and it's wireless. Okay, so I'm wearing the headset. Once I run this Python code I made, it should show my brainwaves scrolling on a graph. So let me just run this code. That's freaking sick. Okay, basically this graph shows the raw electrical values that this electrode is picking up. Now on this graph, I want you to pay attention to this baseline value. The baseline value is important because it kind of compares my current brainwaves to previous brainwaves in this sequence of the last few seconds. Now, the reason that's important is because if that baseline value is elevated, the program recognizes that as me being more focused. If the program recognizes that I'm more focused, it'll signal the Arduino to close the finger. So let's do a live demonstration. Once I plug this finger in, it should close at first, simply just because I'm talking. So let me zone out. Open. And then close. So it works somewhat well, but as you can see, now that I'm talking a lot, it's going to malfunction. But if I zone out, close, it kind of works. So it's pretty 50-50. Zone out, open. So it works-ish, but not great, as you can see. So let me just unplug this. Okay, awesome. Now all I have to do is clickbait the title, you know. First YouTuber to invent telekinesis, and that's the end of the video. Thank you guys for watching. Well, no, I feel obligated to make something that works way better than that finger I built, and to do that, you guys need a better understanding of the brain and electroencephalography itself, so come on. So first let's go over why this finger doesn't work so well, then we can use an analogy to sort of explain how we can make it better. So the finger uses an attention-based spike detection algorithm. In other words, it's not targeted towards when I think about moving my finger, the finger will move, but instead, it's looking for sudden changes or spikes in brain activity. So the finger can open or close while doing literally anything. Take a look at this picture on screen. This is an image of an EEG or brainwave signal. The program can't necessarily differentiate between this spike being close the finger or this spike being brush my teeth. Here's a graphic I made that explains it a bit more in depth if you want to pause the video and take a look at it. And that brings us to the big problem with EEG. Okay, let's put it this way. Imagine you're scrolling on YouTube and you click on a video. Well, when you click on that video, a YouTube server has to broadcast that video to your phone. Well, think of your brain as that YouTube server and your phone as the EEG headset. Now, despite the server broadcasting the video on 4K, your phone is on McDonald's Wi-Fi, so it's receiving the video in 144p. It's the same thing with your brain and the EEG headset. There's electrical activity going on in the brain, but the EEG headset doesn't have a direct connection to it. Now, on top of that, the electrode on the headset doesn't just pick up electrical activity from the brain, it picks up all electrical activity in the area. So things like your eyebrows moving and blinking interfere with that signal. That would be the same as when you click on that YouTube video, clips from another video you didn't even click on popped up in the video feed. Overall, that's sort of what a noisy EEG signal looks like. So what can we do to get a cleaner signal? Well, we can build a denoising pipeline to try to remove any noise or corruption and clean up the data so we can extract features from it and make it easier for our machine learning models to interpret. It's really not that complicated. It's just a few machine learning models, and don't worry, I'm not going to do anything boring like go through the whole process of how I made it or the code. First, I designed a denoising pipeline based on this research paper by Benjamin Choi. Okay, so take a look at this picture on screen. It's pretty much just a test I did on my original denoising pipeline with data I collected of my own brainwaves. Now, as you can see, this original pipeline struggled with localized artifacts. Now, what I mean by that is pretty much the model struggled with these giant spikes caused by things like blinking. In addition to that, the model attempted to denoise the entire signal, even parts of the data that appear to be clean. So if you look, it denoises this first part of the data, and sometimes that can remove features from the brainwave signal that we need for intention classification. So that's really important when it comes to opening and closing a prosthetic arm with your mind. Now, as I said earlier, it struggled with localized artifacts, and if you take a look at this, it did attempt to denoise the signal generated from blinking, but because it attempts to denoise the entire signal, it incorrectly reconstructs the signal later down the line after that artifact is presented. So what I have pulled up is the architecture of the LC classifier I coded. All an LC is a hybrid combination of an LSTM and CNN machine learning model. Let's take a quick look at a graphic to explain more about what it does. So this is a simple graphic to explain what the LC does. An LC works by identifying shapes and patterns within an EEG dataset to identify levels of noise. So as you can see in this graphic, there's 4 types of EEG data: clean, mild, strong, and random levels of noise. In this case, the blue line represents the noisy or corrupted EEG dataset, and the orange line represents the clean EEG data. So as you can see, each type of data is fed into the LC model, and then the LC will predict what level of noise is on the dataset. So if you take a quick look at the right side of the graph, the LC runs a prediction and gets clean for this clean EEG dataset, it gets mild for this mild dataset, and so on. One quick thing to note is this new updated pipeline no longer attempts to denoise the entire signal. Basically, I added a clean signal bypass to the LC part of the pipeline. What that means is any data detected as clean by the LC classifier is no longer denoised. Now, this is useful because it no longer denoises clean parts of the data that may have important features for intention classification later down the line, which is super important for identifying whether someone wants to open or close their prosthetic arm. So this is the script for the architecture of the second half of the pipeline, or the at-to-app model. So this is a quick graphic that explains the entire pipeline and how the at-to-app model works. So basically, the at-to-app or autoencoder's job is to reconstruct the signal. So if you take a look at this graphic, there's a noisy EEG input, and that's passed through the LC classifier. Once the data is passed through the classifier will then label it with how much noise it predicts is on the signal. Once it's labeled, that gets passed through the autoencoder. The autoencoder compresses the signal, keeping important features of the original brainwave and then reconstructing it without noise. So as you can see, the entire pipeline goes from a noisy EEG signal to a denoised EEG signal. And then this is just a quick graphic to kind of show what it looks like in real time. So the orange line shows a noisy or corrupted EEG signal, then the blue dashed line shows the clean reference point. Then lastly, the green line shows the autoencoder's reconstruction of the noisy signal. So as you can see, there's all this noisy data, then the autoencoder reconstructs it similar to the original pattern. Now, I trained this whole pipeline using the EEG-denoise.net dataset. It's basically a dataset of clean EEG data, but it also has data from the electrical activity from muscles and eye movements. I combined those three types of datasets to create my own synthetic noisy EEG signal, then trained the entire pipeline to denoise it from there. And I also tried testing a few other systems, but this pipeline worked best for me. And when I say test, I mean I really tested it. Each of these pictures are graphics I ran on the pipeline to see how it performed at denoising in different scenarios. Not just that, but each of these files and folders all relate to code, graphics, and other things generated as a part of this entire denoising project. Okay, so let's take a look at a few of the results. This is a graphic that shows how the model performed on heavy amounts of noise. So the orange line is the noisy data, the blue line is the clean EEG signal, and the green line is the model's reconstruction. Now, the model reconstructs the signal at about 72% accuracy, and on average it gets in between 70 and 80% accuracy on stronger signals. Now, although that doesn't sound great, this is unrealistic for most scenarios regarding EEG data. Now, this is a graphic on how the model performed on mild levels of noise. So as you can see, it performs a little bit better and gets on average in between 80 and 90% accuracy. This is a bit more realistic of what would happen in real-world scenarios using an EEG headset, but still, these levels of noise and these many artifacts back to back are still somewhat unrealistic. Despite this, the model still achieves a relatively high accuracy. This is another example of the model performing on mild noise. In some cases, the model was actually able to achieve a nearly one-to-one reconstruction on some of the heavier levels of noise like mild and strong. Once again, this is another example of that happening on a strong level of noise. Lastly, let's look at how the model performed on random levels of noise and a clean EEG dataset. So the model performed the best on random levels of noise. And this is a more realistic example of what's going to happen in a real-world scenario wearing an EEG headset. And as you can see, once again, the model performs very strongly on random noise, achieving nearly a 96% correlation value from the reconstructed signal compared to the original. And this is how the model performed on clean EEG. As you can see, the model didn't perform any reconstructions, which, like I said earlier, is really good for preserving certain features for intention classification. Now, if any of that was confusing or you have any feedback for the video, please leave it in the comments below so I know how I can improve for future videos or answer any questions you have. Now, if you enjoyed this style of content, please like and subscribe so I can work towards continuing this series and working on more projects in the future. So I'm going to be doing this as sort of a short series with EEG and working on other few projects related to EEG as well, so they're mostly software focused. But if you have anything you want me to build, please leave it in the comments below and who knows, I might build it. And lastly, if you made it this far in the video, I'm so very grateful and thank you for watching. One thing I'd like to add is a big thanks to Michael Reeves and Stuff Made Here because they've been sort of an inspiration for me to make this style of content and get my work out there. Anyways, thank you guys so much for watching and tune in for the next video.